Hello, I'm going to talk to you today about this automatic tool change spindle that I built. And I used a Jianken JGL 110 4.2 kilowatt spindle that goes up to 24,000 RPM, and it holds BT30 tool holders. So I set it up so far as just a manual tool change. So I am the tool changer, and I wrote a little G-code program to do a tool change, spool up the spindle to 24,000 RPM, and then quit, just to show you what the cycle looks like. So I have the G-code program loaded here, so I'm going to hit run, and it runs up to the tool change, which is in my case line 25, pausing. So press the button back here. Wait a second. Okay, here's the tool holder. Put the new one in. And we are good to go. And then hit run. Takes a little while to spool up. Give my settings. But it's nice and quiet. A little scary how fast it goes. But then runs 15 seconds and it quits. And there we go. So in terms of the ATC, there's a spindle. Up here is all of the pneumatics, and the blue lines are the blue lines here are the coolant. And back here I have the VFD drive that has for the spindle, as well as the associated electronics. So let's go to the details.
So in general, I wanted to add an automatic tool change to my CNC router, primarily so that I didn't have to set the height of each of the tools every single time I needed to change tools when trying to make a part. So to that extent, I wanted variable speed. I wanted enough horsepower to drive, let's say, a 3/4 inch bit, and then also have decent torque sort of at the lower end range, like around 5,000 RPM or something like that. And so here's the kind of specs on the ATC tool holder, and it runs off of 240 volts AC, so it can run in my garage. Some more interesting stuff is that it needs to maintain a max temperature of 60 C, and it's water cooled, so you have to take care of the water cooled portion of it. So here is what the implemented spindle looks like. In terms of the VFD, or the variable frequency drive, here on the left, that's the one that was that I got from the supplier of the spindle, or I bought it through them, essentially, as well as power supply, braking resistor, my electronics, all that kind of stuff. So this box here is actually on the gantry for the CNC router. It's kind of on the heavy side, but unfortunately the total distance that I was given, or that I should have from the variable speed drive to the motor, is only 2 meters. And I guess that's driven by the 800 hertz max operational speed. So that's the box. Then the actual pneumatics and control are here on the right hand side. So there's the spindle clamped to my Z-axis, as well as the dust collection boot that I made here on the side. So up here at the top we have the air lines in orange, and then the lines in blue are the water supply, and then this big cable here is the actual power. So interestingly, when I read the requirements for the cable coming out of the variable frequency drive, it resulted in a rather thick, heavy cable, shielded, of course, going to the spindle, but then the actual spindle's cable is quite a bit smaller, which I found interesting. Anyway, so then, yeah, let's go to the next stuff. So here's the back of the spindle with all of its different connections, and then this is what it looked like when I unboxed it from the manufacturer. And I was mentioning the torque curve here. Down in the bottom is the is the diagram of the torque for the speed. Note that it definitely gets warm if you run it at really slow speeds. In terms of run out and the operation, it is really nice. It is beautifully quiet and smooth when it runs. Kind of makes me grin, though it is a bit big. That spindle weighs, I would guess, almost like 50 pounds. Anyway, so then in terms of variable frequency drive, this is what it looks like, and with the requirements for how much cooling around it. And so that I was easily able to accommodate that by using that big box. Here's what the back of the drive looks like in terms of connecting up to it, and then all of the specific settings that I have used for setting the configuration for the device. I'm using a roughly 0 to 10 volt analog voltage input that comes from the Arduino to drive the speed. And one key issue is that if you actually want to view the error or inverter fault output, so that is a digital signal, then you don't have enough I/O to actually watch and look for a detection of when the spindle actually reaches the programmed speed, which is kind of a bummer. At the moment, it does have an analog output which you can use for that, but I haven't yet done the programming to implement that functionality. So here is the actual full spindle diagram that I drew up. It includes pneumatics and the microcontroller, the VFD, and all the associated key connections between everything. And that's actually what I built. And I'll go into each of the sections separately. So here is the pneumatics portion of that diagram. And we have the spindle, and unfortunately it has 4 different inputs, and not only that, there are 3 different air pressures required. So we have stuff for removing the dust, but then you also have the pressures for actuating the clamps and stuff. So that results in that mess of controls up on the top. Also, there's a very specific set of sequencing that you have for grabbing the tool and releasing it. And so that's what the solenoid valves are doing. Other functionality that I have on here is that there's a switch, a solenoid valve. It's this type down here, the brass solenoid valve that disconnects the air to the spindle in the event where the spindle's turned off. So that's a normally off spindle, so that solenoid's only activated when the spindle's running. Then I have a sensor here which detects if I have air and essentially don't turn on the spindle if I don't have air present. Unfortunately, that simple sensor switch that I first used didn't work well. The accuracy is really poor. I'm not sure if I'll have to work on either replacing that or with something better, and or with something that's maybe not broken if the current one is broken. So another sort of weird problem that I had was that when I would power down the spindle, I would disconnect the AC supply to the whole thing. And when I did that, the 24 volt supply actually would maintain for some short period of time the 24 volt output. So what would happen is that when I shut off the power, it would glitch, and the solenoid valves would then release the tool and open and release the tool and drop it on the floor or on the table, depending on where my gantry was located. As a result, it turned out I had to add a relay in series with all of the solenoid valves so that when the thing shut down, the power to those solenoids was disconnected. Note that when the tool is in the spindle and running or whatever, the solenoids are deactivated. So it is sort of like a normally off state is to not release the tool. In terms of the control for these solenoids valves, these are all just open drain circuits driving those. So here is the actual implementation or focus on that of those different solenoid valves and the regulators. Note that when you actually open or unclamp, the demand for air is fairly high, and as a result, none of the air pressures are nearly what they were supposedly rated at prior to unclamping. Note that, of course, when it clamps again, then that air demand drops off to something much less. I found that when I'm just running the spindle without clamping and unclamping, just running it, it uses a fair amount of air. I'm not sure what cubic feet per minute actually is. I haven't measured it, but it seems like my compressor, which is like 3.5 cubic feet per minute, is running maybe 30% of the time to refill its tank. So the next is coolant implementation. So what I did for the coolant, which was also kind of a big problem, was I just bought a super cheap Honda Civic radiator off of eBay, and then used antifreeze for the coolant because the manufacturer requests that you put corrosion resistant or anti-corrosion additives to the water. And so, not knowing exactly what that would look like, I just used the antifreeze straight. Then the key issue that I had, I actually went through 3 different pumps. I didn't want, so it's sort of 2 parts. I didn't want to break the tubing from the pump all the way up to the spindle, so I didn't want to have the possibility of having leaks at connections somewhere in the milling machine. This is down on the table underneath the milling machine. Then the second question is the pressure required to drive through that length of tubing. In my case, it's almost like 18 feet to go from here up to the spindle, and then another 18 feet to come back. And that's through all of the cable feed trays and stuff like that. And so you have almost 40 feet of 8mm tubing that you're trying to push the coolant through, and the pump that the manufacturer provided was not remotely capable of doing that. So it turned out in the end that I needed to get this pump, which can actually push 45 psi max. And it's claiming 3.3 gallons per minute, but when I actually pumped through that same line of hose and then measured the amount of coolant that pumped, it really did just about 3 liters per minute given this size pump. In addition, other features that I added was I didn't want that coolant sitting in the motor for an extended period of time when I wasn't using the machine. So when talking to the manufacturer, they told me that it's just the steel exposed to that coolant, so it's not like stainless steel or any particular corrosion resistance in the spindle. So what I did is I implemented an inline flush with air of the entire coolant line. So I have a check valve here right after the pump, and then I have a push button valve over here on the air line, and it joins right here at the bottom. It says air purge connection. And so when I push that button, it pushes air through the whole system and flushes it out, and then that overflow of air comes out through this air exhaust overflow, this little bottle with the antifreeze in it that kind of blew out. So I had it previously filled all the way. That's it for this. Here is the electrical system, and this includes an Arduino Mega plus a custom interface board that I made to fit with the Arduino Mega, and then of course the VFD drive and the spindle. The power supply I used was a 3-part 24 volt, 12 volt, and 5 volt supply. And then the interface with the PLC is the Yaskawa LI01 interface board. In my case, the PLC is the MP3300 IEC PLC, and it only has one slot, and in which case I have this LI01 board in there. In terms of user interfaces, I have an unclamp button in the side of the VFD drive box so that I can push the button, take out the tool, and put it back. In terms of the key interfaces that I had to implement for the Arduino, I have some I/O, which is, so I just have to do some voltage translation. So the spindle's running at 24 volts, so I have to convert that to 12. Of course, I'm driving all the pneumatics. That's 24 volt open drain. The spindle also has a thermistor in it, and so I implemented a circuit for measuring that voltage and converting it so that I could use it with the Arduino's ADC. Then I have an analog speed output, which is roughly 0 to 10 volts, which drives the VFD. And then I have I/O that goes out to the VFD, and the VFD is also 24 volt supply. And so I use open collectors on just a simple 74LS07 open collector output digital device to interface with the Arduino Mega, which of course is running at 5 volt. And then I have some other I/O, which are open collector inputs that are coming from the VFD drive. I also provisioned for an LCD display so I could actually get some readout from the Arduino, basically indicating what state the state machine's at or any errors that it may run into. But I haven't actually implemented that yet. Mainly when I did the debugging, I had the serial interface connected to the Arduino Mega. The cabling I used was actually RJ45 connecting to the PLC, just because it happened to be convenient cable to use and was nice and light. Not sure if that's going to be it. So far it hasn't been an issue, but not sure if vibration or anything is going to be an issue with those connectors. In that, for the analog output to the VFD drive, I implemented sort of two possible paths. One, I did an I2C DAC, which is on my interface board, but I also did just a selection of just using the Arduino pulse width modulation output and then filtering that, and that's actually what I'm using at the moment with a pretty severe second order low pass filter cutoff. So the analog output comes out, I do the second order filtering, and that's actually the frequency cutoff is 3.5 hertz roughly. And then at the actual device itself, or right at the VFD drive, I have another filter capacitor, so it gives me an additional 300 hertz cutoff. So the problem is that I don't want any noise on there to modulate the speed of the VFD drive and cause problems, but at the same time, I really don't need to change it very quickly. Usually for these, for this sort of setup, you just set the speed once, and once it gets to speed, it just kind of stays there. So in terms of the PWM output, here's a little chart of what that curve looks like, and I added deadband on each side because I'm supplying 10 volts, and I know it's on the low end, it's not going to be perfect. So 0.2 to 9.8 volts gives me my full range. Then for the thermistor interface, I took the thermistor is the 3950 style thermistor. That's what's in the spindle itself. So I found a data sheet on that thermistor with its curve, and then put that in a spreadsheet, and then found that if I just supply a 3K ohm series resistor to it, it actually linearizes the voltage on that thermistor really quite nicely. So I used a 4.1 volt reference through the series resistor, and then here on the right is my actual curve. And so I know I don't want, if I do an A to B value on the Arduino of 465, I have exceeded my temperature range. So that's what that turned out to work actually really quite nicely. From a interface perspective, this is in between the Yaskawa PLC and the Arduino. You kind of have, again, this 24 volt translation problem. However, the LIO1 is an open collector output. And so instead of connecting that open collector to 24 volts, I just connected that to a 5 volt supply, or the Arduino's 5 volt supply with a resistive pull-up, and then capacitance to cut the frequency at 150 hertz. I did have initially some problems with noise on those I/O lines, and that 150 hertz RC cutoff really worked well. Fortunately, the rate at which I need to communicate between the I/O card or the PLC and the Arduino is actually pretty slow. This is, because of the mechanical movement of things. So 150 hertz was plenty. In terms of going back the other direction, again, the LIO1 is running at 24 volts, and so I was actually just able to use an open collector output from a 74LS07 to drive the input of the LIO1. And so that feeds back things like error alarms, errors, and that sort of stuff, and actually an acknowledgement that the command to a new speed or whatever has actually been successfully implemented. Okay, from a software development perspective, I divided up the software mainly so that the PLC took care of all the G codes and took care of starting the handshake and that sort of stuff with the spindle, and that all that development was done in Yaskawa's MotionWorks IAC. And then on the other side, on the Arduino, the functionality has its half of the handshake, and then maintaining the state machine for the spindle, taking care of any watchdog timers, actually generating all of the appropriate signals to interface with both the spindle as well as the VFD drive. And then also, of course, the pneumatics actuation. From a development environment, I developed a finite state machine library of my own, as well as all of its associated unit tests, and I did that in Eclipse on Ubuntu, and then used the Arduino IDE to actually put that all together into the final program for the Arduino. That actually then made it possible for me to debug and develop it in the actual hardware. So here is the actual state machine that I implemented for the system. And this was, again, all of this was more complicated than I expected when I started. The initial part here is handshaking, from start up through handshake 2. This is sort of set the I/O lines one way and then another way, and go back and forth with the PLC to ensure that the state, all those lines are good, and that the state machines are synchronized between the PLC and the spindle control. Then the key sort of states here are running, stopped, and then unclamped. And then you have so when it's, of course, when it's running, it's in the running state. And then these in-between states are for when it's transitioning between those main operating points, and then have all these state transitions for the things that could happen, like when you push the button but you don't fully push it and it kind of jitters, or when you're ramping but then you stop immediately and hasn't reached its final speed. All that kind of stuff is covered here. The state machine. Here then, for the spindle, mechanical, is the spindle attachment. And so I bought this bracket from the spindle manufacturer. And when I initially got it, I looked at it and it kind of looked kind of rough casting. And I thought, oh, I'm going to have to bore this out. But once I had it chucked up on a mill, it turned out that it was actually pretty good. And it was quite close to being, the bore was actually very close to being parallel with the back surface. And so all I had to do was mount this up on my Z-axis. And once I had indicated in the spindle so that it was parallel with the Z-axis and perpendicular with the table, then I drilled some tapered dowel pins in 2 places and locked the sucker in place. Note that you can only clamp in a limited area on this thing. This even some of the silver and then the black above is restricted, so you're not supposed to clamp up there. Down below, I had my first project on this CNC was then to make a dust boot for this thing, and it clamps easily down there. Finally, or in conclusion, I haven't finished a couple remaining items that I sort of mentioned below. One is this issue with detecting when the spindle reached its final desired speed, and then the spindle ramp is currently a little bit on the slow side, and so I could probably tweak the settings on the spindle to increase, or on the VFD, in order to improve that. And then I haven't implemented the LCD, but I sort of like, once everything was working, I kind of didn't need it, and so I haven't spent the time really to do that. And then the full-blown automatic tool change, I haven't implemented that yet, but that's sort of a whole nother can of worms in terms of implementing an actual carousel or something like that. And if I don't do a carousel and I just have like a rack, then it kind of uses up my machining space, and so I haven't gotten around to do that. And so still at the moment, it's just essentially manual activity of the individual is the tool rack. From unexpected issues that I ran into, one was that I didn't expect the import tax, so I guess I probably should have. It was kind of on the high side. I was paid like 30% of the price as import tax, and I didn't. So the manufacturer didn't mention it, and I didn't get that bill until the spindle arrived in customs. The coolant pump, as mentioned, wasn't nearly the right size. Let's see, covered the I/O problem. The debugging of the pneumatics was unexpectedly difficult. I think I definitely would want to fiddle with those in advance. You would think, hey, it's just you apply voltage and it turns off the supply, but those particular types of pneumatics they're like self-driving, so they can act really quickly, but that sort of complicates how they behave. So I'd fiddle with that. Yeah, I'd fiddle with those a bit before trying to implement something. Then there was also a problem with those style of solenoid valves and the shutoff, or the main shutoff, and that would get locked in a funny state, probably because of that self-driving sort of mechanism. And you'd have to disconnect the air in order to reset it every time you started the machine. So I had to use that different style of solenoid valve. Then we already covered the glitches on the solenoid valves when you power down. The handshake procedure really was required. And then the I/O, I ran into problems with glitching velocity commands. And so that, having 2 parts of it, one is the filtering, and the second one is that the PLC sets a digital word for the speed, and then triggers a flag that also lets things settle and make sure that you don't have noise on the voltage setting. And that is all. Hopefully this will be useful for you.